Hello polynomial fans, this is Mr. Ray with our next lesson in our polynomial equations unit. Today we're going to be looking at title of the lesson is factoring polynomials. So I'm going to introduce a couple of new theorems which are basically rules and tools we can use. Add that to what we've already been looking at this unit and combine everything together to be able to take a higher degree polynomial above a quadratic, like a cubic, quartic, or degree 5, or even higher. We'll probably be only looking up to degree 5 at the most, but we will now have the tools to be able to fully factor any polynomial. Might take some time, but we're going to show you how to do that today. So the definitions here, you've seen these at the last lesson when we did dividing polynomials, either through the long division method or through synthetic division. So just a reminder of what those are. Now, I was just looking at the key concepts here. I basically took this from our textbook, and I got to admit it's a little confusing. So I've made a decision to maybe ignore this, and I've created kind of a new kind of summary that hopefully makes more sense. So I'm going to go through and explain that, and it might not make total sense right now, but we're going to come back to these, and we're going to be using the factor theorem and this theorem here to be able to come up with possible factors fairly quickly and efficiently. So I'm going to start off with basically capital P of x. That just stands for any polynomial function, and you know what those are. So we've seen when we did our division, when we took a polynomial and divided by a factor, if we got a result, if we took the remainder of that, if that remainder was 0, we knew that, well, that divides in evenly, and then we learned that x minus b is a factor. But we didn't actually talk about this, but we can actually determine the remainder very quickly without fully dividing out either synthetic or long division by just plugging in the value of b that we want to check to see if it's a factor. So, for example, whatever I get when I do this division, if I find the remainder, I can actually get that very quickly by just plugging in the value of b back into the polynomial equation. So if all I'm looking for is the remainder and I don't care about the rest, the quotient, all I have to do is plug in whatever value of b is into the original polynomial equation, and the result will be the remainder. So that may not be that interesting in most cases, but if we find that the remainder is 0, if p of x is 0, then we go down to this theorem that's actually much more useful. So the remainder theorem basically creates this factor theorem. So from now on, I mean, this is what you'll be using, but you kind of have to know this in order to get this, okay? So what this factor theorem tells you, we use it to test for zeros or factors of a polynomial. So basically now we know if we plug in a value b into the polynomial and we get a result of 0, that means that x minus b is a factor. So that's pretty useful. We can very quickly go through, well, fairly quickly go through a set of numbers, integers, and try it out. And if we get a result of 0, we know that x minus that number is a factor. And if we put fractions into here, for example, not everything is going to be an integer. So if that was like 1/2, if we plugged in 1/2 into the original polynomial and we got a result of 0, that would mean that 2x, so that's a 1, that's a 2, 2x minus 1 is a factor. So that's where we can find those factors that have a leading coefficient other than 1 for the x. So that's very useful, and we're going to be doing that, but the next question is, well, how do we decide which numbers we should test? You don't just want to start at, 1 and work your way up to whatever, or start at -1 and work your way down. And what about fractions? Like, we just randomly test? Well, this next theorem here, you don't have to remember the name, just really what it does. This actually finds candidates to test. So what we're going to do is, after we do this, we're going to be able to find a finite list of integers and fractions, rational numbers, that we could try using a factor theorem. So if there's any factors, it'll be in this list. Now that doesn't mean every number in this list is going to be a result of 0, but it certainly will trim down the number of possibilities. Okay, so the way we do that, and we're gonna apply these in the example, so don't worry if this is too much theory for you. You'll see how it works. If we had the polynomial, this is p of x again. So what we're interested in is the leading coefficient of the highest degree term, of course, and the constant. So what we do is, the first thing we do is we list off the factors of this capital A, all the factors of the leading coefficient, and a lot of times that might just be, might be 1, and there's the only possibility is 1. Okay, and we also do the same thing with the constant. So we take the number that's there and we list all the possible factors, plus or minus, of that number. So we get that list. Here's the factors of the leading coefficient. Here's the factors of the constant. And then if we put these two together, the only possible candidates for zeros are x equals, and we go through the list of the constant factors divided by possible leading coefficient factors. So sometimes this list is pretty small and sometimes it's pretty big, but at least we've narrowed it down from all possible integers and rational numbers. So this is just saying these numbers came from these two lists of factors of A and C. So you kind of get the idea, hopefully. We're going to actually apply that. So I will include this note on the completed lesson note. I'm going to insert it after the first page, just so you've got a good resource. Personally, I would probably just cross these key concepts. I'll probably change it for future classes. It just it sounds pretty confusing when I look at it again. Okay, so let's start off with some examples. And the first one, it says, determine the remainder when x cubed plus 7x squared plus 2x minus 5 is divided by x plus 7. So this is where we would actually use the remainder theorem. So if we go back to what that said, it said if we plug in, so if we're trying to find the remainder of a polynomial divided by x minus b, all we have to do is figure out what the b is and plug it into the original equation, calculate that, simplify it, and that is the remainder of this division. Okay, so we're going to do that. Now, this isn't actually written as a function. Okay, so I would like to put it in function notation. So it's not just an expression. So this is p of x is equal to that, and we're dividing by that possible factor, linear factor. So if I'm looking at this, okay, remember we have to get it in the form x minus b. Sorry, down here. We have to get in the form x minus b. So we have to, use that reverse logic we tend to always do with quadratics. For example, when we're looking for the vertex, it's actually, you could rewrite it as x minus. Now what number would go in here to make that x plus 7? It would be negative 7. So that means your b value is negative 7. So I think most of you probably understand that because you've seen it so many other times. But if I'm trying to divide by x plus 7, I'm going to plug in p of negative 7 because that's the value I'm testing. So we go right into function notation. Actually, I'll rewrite the original function first just so you can see each step. So p of x is x cubed plus 7x squared plus 2x minus 5. And we want to find the value of plugging b into here, so that would be p of negative 7. Okay, and so it's basically wherever you see an x, you change it to negative 7. Okay, and I'll do this math fairly quickly. So that's negative 343 because it's a negative being cubed. This is going to be positive 49 times 7, which is positive 343. So that's encouraging. And then we have minus 14 minus 5. Okay, so these two actually cancel out, so that simplifies the math, and I'm left with p of negative 7 is actually has a value of negative 19. And based on the remainder theorem, we know that's the remainder when we divide p of x by x plus 7. So therefore, the remainder, just make this official, of, and I'll just use p of x now, p of x divided by x plus 7 is negative 19. And you notice when you use the remainder theorem, you actually don't get the quotient, the result of the division. All we're getting is the remainder. But it does save some time because then we don't actually have to do the division. If I would want to find the remainder when the p of x is divided by, say, x minus 10, I would calculate the value of p of 10. So I'd plug in 10, whatever value I get here, that would be the remainder of that division. So it's just changing the value you're testing for. Okay, so the next one, we're actually using the factor theorem now. So we're actually checking, we want to know which of these are factors of p of x. Okay, now this is a different p of x than that. And the way we do that is we use the strength of the remainder theorem. So if I want to know if this is a factor, I'm going to test for p of 2. And that's going to give me the remainder when p of x is divided by x minus 2. Okay, so if we go through that, if I plug the 2 in there, I won't, so that I'll just talk through the first one. So that's going to be 2 times 2 cubed, so that's 2 times 8, which is 16. Plug the 2 in here, 3 times 4 is 12. Then negative 3 times 2 is negative 6. And then negative 2 by itself. Well, that totals up to 20. Okay, well, the fact that that's not 0 just means it's not a factor. Okay, the actual value, I mean, we're not going to do anything with the 20. The fact that we're only looking for, is it 0 or not 0? Okay, now if I want to, so we know x minus 2 is not a factor. Now if we check for x plus 2, this time we plug negative 2 into the function p of x. So p of negative 2. So this time we're going to get negative 16 plus 12 plus 6 minus 2. We combine all these two together, we got 8 positive 18, negative 18. That actually does equal 0. So this is a factor. Okay, and if we want to check for x plus 1 being a factor, we plug in negative 1 into p of x, so p of negative 1. So this time we're going to get negative 2 plus 3 plus 3 minus 2, and that's equal to, we got a 6 minus 4, that's equal to 2. So the fact that that's not 0 tells us x plus 1 is not a factor. Okay, so we got 1 out of 3 so far. Let's try x minus 1 as a factor. So that means we test p of 1. And when we plug that into the original polynomial function, we get 2 plus 3 minus 3 minus 2. That's positive 5, negative 5. This does equal 0. So that tells us it is a factor. Okay, now this time we're testing for a, something that's a factor that's got a coefficient in front of x other than 1. So if you remember, you're basically finding the zero that would create if that factor was, if that was a factor, what would the zero be? So, and that's what we plug in. That's what we've been doing all along. So in this case, if you basically set this equation equal to 0 and then solve for x, you're going to get p of -1/2. And you can always test out, plug -1/2 in here, you get -1 + 1, that's a 0. Okay. That doesn't mean this is a factor until we actually find the value here. But this is the 0 we're testing for. Okay, this one's a little trickier because of the fractions. We're going to get -1/4 plus 3/4 plus 6/4. So the good news is it's all quarters minus 8/4. Okay, so if I just add up the enumerators, I've got 9, positive 9, and a -9. So that does equal 0. So this also is a factor. Okay, so that answers that question. Part B says, use these results to write p of x in factored form. Well, what do we know about p of x from this? Well, we know this is a factor, x plus 2, x minus 1, and 2x minus 1. Those are all factors, so you could rewrite it in factored form. Doesn't matter the order. Multiplication is can be in any order. It doesn't change the outcome. So I'll just put 2x plus 1 as my first, and then I'll decide, okay, let's put x plus 2, and then x minus 1, just because I felt like it. Now, question is, how do we know there's not more factors? Because we found these 3, but who's to say there's not more? Okay, well, that's an easy question to answer because you could see if you multiplied all these x terms, that's 2x times x times x, that would be 2x cubed because you got 1, 2, 3 x's you're multiplying, and that gives you your first term. So there's definitely not any more factors. We've got three linear factors, and that's going to create a cubic every time. So that means we're done, and all we had to do was grab these 3. But it could be possible, maybe we didn't test for a factor that was really a factor. So you can kind of tell by the degree, are we creating that degree through these factors multiplying together? Okay, so this is the polynomial in factored form, and you can see the power of this. Now that we know this, we can find the zeros and the degree of the zeros and do a much better job of sketching. We'd also have the end behavior, the y-intercept, and we just use our knowledge to create a nice sketch from that. Okay. Now, the past question, they gave us some factors to try out. So what if you don't know what to try out? Well, this is where this theorem comes in. Okay, this is where we find candidates to test. So remember, we're looking for the factors of the leading coefficient and the constant, and then we go from there. So list the possible values of x that could be used for finding factors for the given polynomials. So I'm going to write underneath each of the leading coefficient and constant the possible factors. So when it's just x squared, I mean, it could be a plus or minus 1, obviously. I'm just going to put 1 because I'm going to make these plus or minus. So when I have a 6, that could be plus or minus 1, 2, 3, and 6. Those are all the factors of 6. And since capital A here, the coefficient, leading coefficient is 1, we're just going to leave it like that. Okay, so remember, we can make all the possible candidates by, remember, it's going to be these numbers over these possible numbers. And since there's only one possible number here, it's really just repeating this. So the test values that we should try include plus or minus 1, 2, 3, and 6. Okay, so hopefully you get the idea of that. So this one, so the 5 didn't matter at all. And you can actually look at this. This is a simple trinomial. You actually know the factors are x plus 3, x minus 2, x plus 3, x plus 2, which means the zeros would be minus 3 and minus 2. And you can see those numbers are there. But there's some candidates, obviously, that aren't going to be zeros. But you know for sure that if there are factors, they're going to be in this list. So then it's just a matter of going through the list. Okay, now this one here again, we just have a 1 because it's a leading coefficient of 1. The negative 24, we've got plus or minus. So these would be the factors 1, 2, 3, 4, 6, 8, 12, and 24. So there's a few more here. So test values. Now since that's a 1, that makes life easy because it's really just this list now. So just repeat what that one was. Plus or minus 1, 2, 3, 4, 6, 8, 12, 24. Now that's a pretty big list, okay? I admit that, but at least it gives us some ideas to test. And when we test, we're always going to start with plus or minus 1 and work our way up the list. So this one here, x to the 7 plus 24, so leading coefficient's 1 still, and we've actually got the same list as we had here. So instead of writing it out again, so this polynomial would have the same candidates to test as this one. Even though the degree is different, the fact that the leading coefficients and the constants are the same, even though that's minus, that's plus, it doesn't make a difference. Okay, so test values here, same as before. Plus or minus 1, 2, 3, 4, 6, 8, 12, 24. Okay, now we get to some trickier ones where we've actually got a leading coefficient. So now we've actually got 1 and 2. And here we've got our traditional 12. Actually, we haven't had 12 yet, have we? No. So 1, 2, 3, 4, 6, 12. Okay, so this is how this is going to work. So to begin with, we actually have to try all of these with the 1 as the denominator, and then we try all of these with the denominator dividing by 2. So these don't have to be in ascending order. It's pretty hard to do that on your first attempt, but we do know we can start with this list as it is, 1, 2, 3, 4, 6, 12. Okay, so we've covered off the 1 because we just used each of these numbers divided by 1. So I forgot the plus minus. Now we actually go through and do 2. So it's each of these divided by 2. And we've already put the plus minus out in front, so we don't have to repeat it for every number. We know these are all positive or negative. Okay, so the first thing we do is look at the 1 here. So it'd be 1 divided by 2. Well, that's not in our list, so I'm going to add that as an option. The 2 divided by 2 is 1, but it's already there, so we don't have to add it again. 3 divided by 2, well, that's new. Okay, 4 divided by 2 is 2, but 2 is already in the list. 6 divided by 2 is 3, 3 is already in the list. And 12 divided by 2 is 6, and 6 is in the list. So sometimes you're going to get a lot of repeats when you divide by something else here. We just added 2 rational numbers in this case. Okay, so this is similar. So here we've got, now this time we've got 1, 2, and 4, and here we have plus or minus 1, 2, 3, 6 for the negative 6. So test values could be, again, let's start off with that, dividing by the 1. So it's plus or minus 1, 2, 3, 6. And now we divide by 2. So, sorry, we're dividing by that 2. So it's 1 over 2, that's new. 2 over 2, we've got that there, 1 already. 3 over 2, that's new. And 6 over 2 is 3, but we've already got 3. So now we've covered the 1 and the 2. Now we do the 4. So that's 1 divided by 4. That's definitely new. We have 2 divided by 4, which is 1/2, but we've already got that. 3 divided by 4. 3 divided by 4 is new. And 6 divided by 4, that's 3/2, which we already have there. So if whatever factors this have, it's going to come from these possible zeros. So once we know, we can start, a testing. And like I said before, we're always going to start with plus and minus 1 and then kind of work our way through. Hopefully you don't have to do any more than 4 or 5 of these, but it's, sometimes it is possible. You only sometimes you only get your first possible factor after you've done it, 4 or 5 times. So it's frustrating, but it definitely does happen. This one's a little simpler. So this one, they both have 1 and 1. Okay, so the only possible test value or values, because it's plus minus, is 1 over 1, which is 1. So plus or minus 1. And this is actually a sum of cubes. And that factors into x plus 1 and then a quadratic factor. Okay, so sometimes you'll actually know which ones to test for, or sometimes you can use something from previous knowledge. Okay, so now you've found some you know how to find candidates, you know how to test the candidates, and once you test the candidates, you know how to put a polynomial into its factored form. So what we're going to do here is, this is the big moment. This is where I give you something that's something above a quadratic and ask you to factor it completely. I didn't ask to sketch it, but that could be kind of a second part of the question. So again, this is going to be, it's not written as a function, so I'm going to write it as a function, p of x. I like using p of x because think of polynomial. It's a polynomial when you see p of x. So I'm just rewriting it here. Okay. So if I'm thinking about test values, that's the first step you do. What are the candidates? So again, here we've got 24. It's pretty popular. We've seen it before. 1, 2, 3, 4, 6, 8, 12, 24. So quite a few. And luckily this is just 1. So it's really just those numbers there. So I'll just put up my entire list here. So plus or minus 1, 2, 3, 4, 6, 8, 12, 24. Okay, so now we've got our candidates. Like I've said a couple of times already, we're always going to start with plus or minus 1 and hope it works. It's not a guarantee. So the first thing I'm going to try is p of 1. So it's basically plugging in 1 into here. Okay, and when I do that, that's going to be 1 cubed is 1. 5 times 1 squared, that's, sorry, negative 5 times 1 squared is negative 5. Negative 2 times 1, and then plus 24. Well, that's equal to 18. So what does that mean? That means that this doesn't give you a 0 or a factor, so we keep going. So let's try p of negative 1. And I'll just write in the result here, negative 1 minus 5 plus 2 plus 24. Okay, and that's equal to 20. So again, that didn't work. A lot of times it does. It didn't this time. So we keep going. Let's try p of 2. So working our way through the list. Okay, so P of 2 is 2 cubed, 8, minus 5 times 4 is minus 20. Negative 2 times 2 is negative 4, and plus 24. And unfortunately, it doesn't look good. So we've got, this works out to 8, because these 3 cancel out. So again, that didn't work. So don't get too down in the dumps. Just keep plugging away. It will eventually work. P of negative 2. Okay, so this time we get negative 8 minus 20 plus 4 plus 24. And you can see I've got a, what have I got here? I've got a 28, positive 28. Well, that's a negative, sorry. A negative 28, sorry, positive 28, negative 28. That means good news. That means P of negative 2 is 0. So that's the remainder. That tells you that. Put it up here. X plus 2. And remember, it's x minus this number. So it's x plus 2 is a factor of P of x. Okay, so does that mean we have to keep going to find the other ones? Actually, it's good news. It doesn't, because if I know this is a factor, okay, I can actually divide it out from this cubic, and you know I'm going to get a quadratic left over. So there's no point in keeping going. A lot of times you just need one of these, and that gets you down to a quadratic factor that you can handle in the ways that you learned in grade 10 and 11. So we have to do our division. So I'm going to do a synthetic division. So remember, it's the coefficients that we put across the top. So that's 1, negative 5, negative 2, and 24. And we already know we're going to get a remainder of 0, or we should, because we've already found the remainder when we did this. Okay, and what are we putting over here? We put the actual value that the 0 we're trying to test for. Okay, or you could just do the solve this factor if it's set to 0. Okay, now if you remember this, okay, now you could still do this with long division, but it's going to take up a lot of room. So you bring down the 1, and then you multiply the results down here by negative 2 every time. So that gives us a negative 2 here. Add them together. Okay, and then multiply this by negative 2, we get a positive 14. And add those together, we get a 12. And then multiply the 12 by negative 2, we get negative 24. And good news, that confirms that the remainder is 0, which kind of knew it should, but at least it confirms our division was correct. Okay, so what does this all mean? Well, now I can actually rewrite P of x into 2 factors, this factor and basically the result, the quotient of this division. Okay, so that's going to be x plus 2, and now we got to convert this 3-term, this is a trinomial, into something with x as an x squared. So we know that first term because we're dividing a cubic, that the quotient is going to be a quadratic because we are dividing by something degree 1 linear. So this is going to be 1x squared, or just x squared, minus 7x from there, plus 12. And this is where your grade 10 and 11 skills take over. Hopefully you remember. We're going to factor that. That's a simple trinomial. So hopefully you remember. It's going to be 2 factors. We'll start with x, multiplies to positive 12, adds to negative 7. It's going to be negative 3 and negative 4. So there is your fully factored version of the cubic. This is the first time you've ever been able to factor something higher than a quadratic. Okay. Now, don't forget, if you get a quadratic left over, it doesn't necessarily have to factor. Hopefully you remember that. So that doesn't mean there's no zeros. Okay, these could be, you might have to plug this into the quadratic formula. If you can't factor it immediately, plug it into the quadratic formula, and that's going to confirm if there are any zeros, like if you have to graph them, or if maybe there are no zeros. Maybe it's maybe you get the negative in the square root, b squared minus 4ac in the discriminant. So that's it. That's how you do it. So this, like I said, this is a very important question where I just give you some raw polynomial of degree 3 or higher and ask you to factor it. So if you look at what we did, we came up with the test values to test possible candidates to test based on the factors of the leading coefficient and the constant. And then we kind of methodically went through until we found the one that actually gives you a remainder of 0, which means it's a factor. So this here told us that x plus 2 is a factor. Once we had that, we then used our division to figure out, well, what's the other factor going to be since this is a factor. And once we found that, we looked and said, can we factor that? Once you get it down to quadratic, you just use your tools and methods from before. Okay. All right, so we're going to keep going with kind of what we just did. So this time we've got a function f of x, and it's a quartic. So, but if you notice, it doesn't have a constant. So you might think, well, how are we supposed to find the candidates for testing if this is a 0? Because there's no factors of 0. Well, the secret to this is, well, if there's an x in every term, that means for sure there's a common factor here of at least x. So the first thing I'm going to do is rewrite f of x with the common factor taken out. So that's going to be, actually I could take a 2 out as well. It's 2x. So if I factor 2x out, I'll put the result in square brackets. That's going to leave me 2x cubed plus 3x squared minus 3x minus 2. Okay, and now you can see, well, so I've actually already got one factor here, 2x. So I'm going to start working with this. So I'm going to do a little side thing here. Now I can't call this f of x because it's not the same as this. So I'll just give it a new function name, g of x, and we'll work with that. So 2x cubed plus 3x squared minus 3x minus 2. So now we're working with this. So so if I made a list of test values, there's not too many here because I have a 2 and a 2. Okay, so let's do it in our head this time. So I'm going to have plus or minus, well, 1 and 2 from there. And what if I divide 1 and 2 by 2? That's going to give me a half, and 2 over 2 is 1. So those are the only possible test values. And so I'm going to start off like we did before with g of x. I'm going to try g of 1. And when I do that, I get 2 plus 3 minus 3 minus 2. So guess what? We found it on our first opportunity. So what that tells me is that x minus 1 is a factor. So it's a factor of g of x, but there's g of x there. So I can now, I don't really need brackets around 2x, but I want to make it clear it's a factor. So I can put an x minus 1 there, and there's going to be something else here. It's going to be a quadratic. How do I get that? I get it through the division. So I'm going to divide g of x by x minus 1, and that will tell me what was left over. So I'll use the synthetic division. So I'm taking this g of x, so that's 2, 3, negative 3, negative 2, and I'm dividing it by x minus 1, so I put a 1 there because that's the 0. So again, you don't have to use synthetic division, but I highly recommend it. It's quicker and it uses much less space. So reminder of how this works. So we bring this first digit down all the time, and then we multiply the results down here by 1. So 1 times 2 is 2. Add them. 1 times 5 is 5. Add them. 1 times 2 is 2. Add them. And there's your remainder, which we kind of knew ahead of time would be 0 because we knew this was a factor. So this is the result we're looking for. 2, the 5, and the 2. So that's going to be the coefficient of the x squared term of the factor, coefficient of the x term of the factor, and that's going to be the constant. So I can now go back here and write 2x squared plus 5x plus 2. Okay. Now it's possible that might be factorable, it might not be, and I'll just save a bit of time here. It actually is factorable. So if we know it's factorable, we know we're going to have one term with 2x and one term with x. One of these will be a 1, one of these will be a 2. So if I put a 2 there, I'll get a 4x. If I put a 1 there, I'll get an x. So that sounds like a plan. So put the 2 there, the 1 there, and there's our remaining factors. So this is the factored version of f of x, and now we do the sketch like they asked for. Okay, so what does this tell me about the zeros? Maybe I'll just write them down here. I've got 0. Don't forget this one. Okay, that means there's a 0 at 0. At 1, this would be negative a half, and this would be negative 2. So I'll spread these out a little bit. Okay, so I have a 0 there, I have a 0 there, negative a half, so these are pretty tight, and negative 2. And the y-intercept, since I have an x-intercept at 0, that's also the y-intercept, so I don't even have to check for that. What about the end behavior? We go back to our expanded version here. So this is degree 4, even, positive leading coefficient, means I have this end behavior, and I know all these zeros are order 1, so it means they're going to cross through. So this one's pretty quick. I know I'm going to come down from here, go through this, and then I'm going to probably, this is a guess now, halfway between these I'm going to have a little local min, come back up to here, cross through again, halfway between here and here, turn around, come back, cross through, turn around, come back, and there we go. So you can actually do these sketches pretty quick. You need to know the end behavior, you need to know the zeros and their orders. Y-intercept is helpful for sure. Now the only thing that might make this not so accurate is we don't know, like I've said before, we don't actually know the y values of these local mins and maxes. We do know that they're halfway between, but for all I know, it actually could be way down here. So I'm just kind of guessing. And that's the best we can do at this point. If you're taking calculus, this is the one thing. This is one of the things calculus does really well. You can find these local mins and maxes very quickly. Okay, no guessing involved. Okay, so this question here, well, you can kind of tell by the title, use a grouping strategy to factor polynomials. So we want to factor this. So I'm going to start off by actually calling it a function, p of x. That's x to the 4th minus 6x cubed plus 2x squared minus 12x. And if you notice right away, we don't have a constant here, so that's a sign that for sure you can factor an x out. Okay, and that's all you can factor out because of that leading coefficient of 1. So we'll do that first. So I've got x times, I'll put in brackets, x cubed minus 6x squared plus 2x minus 12. Okay, now they want us to do grouping strategy, so I'm not going to do what I did up here and find all the candidates. Sorry about that. I'm not going to look for the candidates for zeros for this and then try to, trim this down to a linear factor and a quadratic factor. It's actually telling me use a grouping strategy. So this is another technique that works more than I thought would work. I see lots of students that answer questions I've given expecting this technique, and they do it with grouping, and it's perfectly legitimate. So obviously it only will work if you have 4 terms in your factor or in your polynomial itself. So let's do what they told us to do. Let's group these. So the x stays outside, so I'm going to use like big square brackets. Okay, save myself a bit of time. I'm going to group it right away. X cubed minus 6x squared plus 2x minus 12 bracket square bracket. And now we're going to remember factor by grouping. We group them and then we find a common factor for each group. So for the first one, the common factor is x squared, and we have an x minus 6 left over. And then we have a factor of 2 here, x minus 6. Now you can tell that this grouping strategy works. This is kind of like decomposition, right? If you get the same factor here, common binomial factor, that means you can continue and finish this. So I'll keep my x there, but I can see I have a common x minus 6 factor, and I also have an x squared plus 2 factor. Okay, so what can we do with this? Well, you can see this is a sum of squares, and there's actually no solution for x that would give you 0 here. So that actually means that there's no real roots. So on the graph, this would just be kind of a, you'd see a turning point like higher or lower than the x-axis that actually doesn't create any extra zeros. So you'd actually only have the 2 zeros, one at 0, one at 6. But they didn't ask us to graph it, they just wanted us to factor it. So, but I'm saying you don't have to do any work trying to figure out if this has a factor, because you can't factor a sum of squares. There's no way this could ever be 0. Okay? All right, last question. And this one's kind of an interesting one. It's going to take you back a couple years. So we have, it says when 2x cubed minus mx squared plus nx minus 2 is divided by x plus 1, the remainder is negative 12, and x minus 2 is a factor. Determine the values of m and n. So at first glance, this, you're probably scratching your heads at this one. Now there's 2 pieces of information. So the first thing I'm going to do is actually make this a function. Okay, so I'll call it p of x, as I usually do. P of x equals 2x cubed minus mx squared plus nx minus 2. Okay, now it says when if we divided p of x by x plus 1, we get a remainder of negative 12. So this is actually providing us a very important piece of information, because this says that if I tested for the 0 here, negative 1, the remainder will be negative 12. And that also means p of negative 1 is equal to negative 12. So it's actually giving me a value on this function, like a point. So p of negative 1 is equal to negative 12. And we're going to use this to actually solve the question. Actually, let me move this over a bit. so I have some room under here. Okay, and it also says x minus 2 is a factor. So that tells me, working backwards with the factor theorem, if x minus 2 is a factor, that tells me that p of 2 is equal to 0. Because if I divided by this, I get a remainder of 0. Okay, so those are 2 points, and that's actually going to help us solve. So first thing I do is plug in this information. Okay, so remember, this is my p of x value, and this is my x value. So this tells me that p of x would be negative 12. So I'm just going to use this piece of information now. So negative 12, like the y value, is equal to, now if I plug in negative 1 for x, let's see what we get. So that would be negative 1 times 2, so that's negative 2. If I plug in negative 1 for x here, that turns into positive 1, so that's minus m. If I plug in x equal negative 1 here, that's minus n, and then minus 2. So you can see I've created a new equation with m's and n's. I can simplify this quite a bit. So what I'm going to do is, that's a negative 4. So if I add 4 to both sides, I get negative 8 is equal to negative m minus n. And just to make it look a little more appetizing, too many negatives here, so let's multiply both sides by negative 1. So, and then switch the sides. That tells me m plus n is equal to 8. So that's interesting. It doesn't solve the question yet at this point, but now we're going to take this piece of information and do the same thing we just did. So that's our first equation that we got from this first piece of information. Now we're going to plug in 2 for x, and we know that the result is 0. So that's my p of x is 0. And now we plug in 2 into here, so that's 2 times 2 cubed, so that's 16. Plug in a 2 here, that's 4, so that's minus 4m. Here, if I plug in a 2 there, that's plus 2n minus 2. Okay, so if we combine the constants here, I get a 14 on this side, and if I subtract it from this side, that would be adding, sorry, it'd be subtracting 14, so minus 14 equals minus 4m plus 2n. Yep. Okay, and we can actually divide both sides by 2. And I'm going to flip them around here. Actually, I'll just leave them. Negative 7 equals negative 2m plus n. And now I'm going to multiply both sides by negative 1 and flip the sides. So I'm going to get 7 comes over here because it's negative, and then I get 2m minus n here. Okay, there's our second equation. All right, so I want you to think back to grade 10. How do we solve 2 equations with two different variables? Well, the answer to that is using a linear system. We got 2 unknowns with 2 equations, so you could graph this. I wouldn't recommend it, or you could use substitution or elimination if you remember. So I'm going to create my linear system here just to repeat what we did. M plus n is equal to 8, and 2m minus n is equal to 7. Okay, now you could use either method. It doesn't matter. I take a look at that and I think this is already set up nicely. If I add these 2 equations, the n's cancel out. So that would be equation 1 plus equation 2. That's going to give me 3m. That cancels, equals 15. Divide by 3, we get m equals 5. Okay, and now you substitute m equals 5 into either equation. I'm going to sub it into 1. So if m is 5, that becomes 5 plus n equals 8. N equals 3. Here's my solution. So therefore, just to summarize, m equals 5 and n equals 3. So that's kind of an interesting question. You'll probably see something like this on a test, where the important part here is converting this knowledge here about the remainder and what you're dividing by into an actual point or value you could use to plug in. And then this one should be a little easier. If x minus 2 is a factor, then p of 2 is 0 for sure. But this one is straight from the remainder theorem. So use these 2 points to create separate equations with m and n left over, and then you just use the linear system to solve. Okay, so got some homework questions for you to try. We covered a lot today, but it kind of wraps up this section in terms of we've been building up a lot of knowledge to get to this point. Basically, I give you a polynomial of degree 3 or higher, and you factor it and then sketch it as best as you can. So that's really the goal of this unit. Everything we've looked at has been kind of leading us towards this type of question, especially the question, where is it? Question number, oh, here it is. Example number 4. This is a very typical question where you'd just start with a function, get the test values, figure out which ones lead to a factor. Once you've got a factor, you divide out, and then you find the other factor, and hopefully you can factor that if it's a quadratic. And then the second part might be taking this into a sketch, which we did on the next couple of questions. Okay, so that's all for today, and see you on the next lesson.